everybody. This is Chapter 4, Section 2 on the basic concepts of probability. In this section, we're going to learn about 3 different approaches to finding the probability of an event. And the most important objective of this section is to learn how to interpret probability values. Okay, some definitions to start. First things first, what is an event? An event is any collection of results or outcomes of a procedure. Now, procedure might sound like a fairly clinical term, but as we'll see, all it really is whatever happens to be happening, and the event is the different outcomes that are the possibilities of that event happening, or of that situation happening, I should say. The next definition is a simple event. So a simple event is an outcome or an event that cannot be broken down into simpler components. For the most part, all of the events that we're going to look at are simple events. It's just a little bit of a clarification because sometimes events can be broken down into even smaller events. Similar to kind of how you reduce fractions from large fractions and you can simplify them, the same kind of thing goes with events. And then finally, last definition is a sample space. And what the sample space is for a given procedure or what is going to happen, it's going to consist of all the possible simple events. So basically, the sample space consists of all of the different outcomes that cannot be broken down any further. And this will make a little more sense as we keep going. So here's an example. In the following display, your textbook uses a small b to denote a baby boy and a small g to denote a baby girl. So what you'll see here is that we have a procedure. And let's look at what that procedure is. In this case, the procedure is a birth, either a single birth or 3 births in a row. Okay, now what are the different outcomes or events that can happen from a single birth? Well, in the case of the first single birth here, we're told that the example of the outcome is that a girl is born. So a girl being born would be a simple event. But for any single birth, the sample space isn't just that you could have a girl, you could have a boy or a girl. So again, the sample space is all the different possible outcomes. Okay, so then let's look at it for 3 births. So this is 3 births in a row. Excuse me while I sneeze. Okay, so let's give an example of what that might look like. 2 boys and 1 girl. Now you could get that a few different ways. You could have 2 boys in a row and then a girl, a boy, a girl, and then a boy, or a girl, a boy, and then a boy. And all of those would be simple events. But the full sample space for 3 births is all the different possible outcomes. So in this case, you could have a boy, and a boy. You could have a boy, and a girl, a girl, and a boy, a girl, and a girl, a girl, a boy, and a boy, a girl, a boy, and a girl, a girl, and a boy, and 3 girls in a row. So there's actually 8 different potential combinations when you have 3 births versus 2 combinations for a single birth. Okay. Some notation that we should talk about. So the first is that a probability is denoted by an uppercase P. And the different events are done using letters of the alphabet. So starting with A, B, C, and so on, depending on how many different events you're looking at. For the most part, we won't go beyond 3 different events, and usually we'll actually only be looking at 1 event or 2. So when you put that into formula notation, you have the probability of your event in parentheses, such as event A here. And what this is telling you is that you're looking for the probability of event A occurring. Okay, there are 3 different rules that we're going to talk about for computing probability. 2 of them are really rules we're going to use, and one of them, as we'll see, is more of an estimate. Okay, so rule number 1 is the relative frequency approximation of probability. So that's a lot of words, but what is it actually? Here we're going to conduct or observe a procedure and count the number of times that event A actually occurs. Based on those actual results, we're going to approximate the probability by using this formula. The probability of event A equals the number of times A occurred divided by the number of times the procedure was repeated. So let's talk through an example on this. So imagine that you have a coin, a penny, and you're doing coin flips. And event A you've defined as getting heads. And so as you're flipping your coin, let's say that you're going to repeat your procedure 10 times. So, and let's say that out of those 10 times, you got heads 4 times. So the number of times that A occurred, which is getting heads, would be 4, and we would divide that by the number of times the procedure was repeated, 10. And if you were to do out that math, you'd find out that 4 over 10 reduces to 2 over 5. And when you do out that fraction, then you would be able to get it in decimal form, your probability of A. Okay, so that's the relative frequency approximation of a probability. And again, this requires that you're actually observing a procedure happening and then counting the number of times that something actually occurs. Okay, the next rule is the classical approach to probability. Something to note, though, here is that it requires equally likely outcomes. So, for example, similar to what we were talking about with the coin flipping example, we know that, let's use an example of a dice instead. So imagine that you have a dice, a 6-sided dice. Each time that you roll the dice, you have the same likelihood of getting any one of the sides, unless of course you're using a weighted die, and then that wouldn't have equally likely outcomes. So imagine that as we're kind of talking through this, a roll of a die. So for this roll, we're going to assume that a given procedure has n different simple events, and that each of those simple events has an equal chance of occurring, just like with the die. We would have 6 different possible simple events, because there's 6 sides to the die, and each of those different sides has an equal chance of occurring. And then we're going to look at if event A can occur in S of these n ways, then the probability of A equals the S number of ways that A can occur divided by the number of different simple events. So, for example, let's talk through our die example a little further. Now, a die has 6 sides. So 3 of those sides are odd numbers and 3 of those sides are even numbers. So let's imagine that what we're looking for is the number of ways an even number will come up. So there are 3 different ways on any die that an even number can come up. It can come up in the number 2, in the number 4, or the number 6. But the number of different possible simple events is actually all 6 sides of the die. But an even number can only occur in 3 of those. So 3 out of 6 means that you would get a probability of getting an even number of 50%. Okay, the final rule for computing probability is called subjective probabilities. And this is where the probability of event A is estimated by using knowledge of the relevant circumstances. So a good example of this would be when you buy a lottery ticket and you say, well, I have a 0% chance of winning, or I have a 1 in a billion chance of winning. Those are using some knowledge of relevant circumstances, such as the fact that it's very unlikely to win the lottery, and guessing at a probability. And really, this is not meant to be at all accurate. It's mainly used when something is either very certain or very uncertain to have happen. And that's why this rule really isn't a true rule so much as it is something that people actually do. But it's not a way that we are going to be looking at probability in terms of actual problems in this course. Okay, a concept that we need to touch upon here is something called the law of large numbers. And what the law of large numbers tells us is that as a procedure is repeated over and over again, the relative frequency probability, or the percentage probability, of an event tends to approach the actual probability. So let's talk through what that actually means. So imagine, again, back to our coin flip example. A coin has two sides, so you have roughly you have a 50-50 chance of getting heads or tails. But the problem is that if you were only to flip that coin 10 times, you may not see that 50-50 equally likely outcome play out. You might get 60-40 or 30-70. But if you were to repeat that coin flip another 100 times, you'd find that as you repeated it over and over again, you'd get closer and closer to that 50% split. And if you were to repeat this procedure 1,000,000 times flipping a coin, you'd find it even gets closer to 50-50. So again, as a procedure is repeated over and over again, the probability actually starts to approach the actual probability. So another example that I want to talk through real quick is, here's our example of, we've already seen this in terms of the table that we saw at the beginning of the PowerPoint, but when 3 children are born, this is the sample space. There are 8 different combinations of how that could play out between having boys and girls. So in this example, we're going to assume that boys and girls are equally likely, and we want to find the probability of getting 3 children of all the same gender. So in order to solve this problem, we're going to have our probability of 3 children of the same gender, or event A, and we're going to look at our sample space. So you get 3 children of the same gender here, not here, not here, not here, not here, not here, not here. Oh, we see it again here. So 2 out of our 8 possibilities result in 3 children of the same gender. And if you were to calculate out the math, you'd find that that's a 0.25 probability, which if you were to multiply that by 100 and turn it into a percentage, would be 25%. So when 3 children are born, the likelihood of getting 3 children of the same gender is approximately 25%. In order to, kind of like what we were talking about with the law of large numbers, sometimes repeating these procedures over and over and over again can be very time consuming. And so oftentimes simulations are used. And a simulation is a process that behaves in the same way as the procedure itself so that similar results are produced. So typically this will be a computer program or something along those lines that will basically run the procedure over and over again. So for example, the computer would come to birth 1. It would make a decision, boy, girl, go on to the next one, boy, girl, go on to the next one, boy, girl. And over time it would calculate all the data, and again, that allows you to be able to simulate large numbers without having to do them yourself. Okay, a couple of other things that are important to talk about with relation to probabilities. Probabilities are always expressed as a fraction or a decimal between 0 and 1. And what that means is that the probability of an impossible event is 0, and the probability of an event that is certain to occur is 1. And all other probabilities are somewhere as a fraction or decimal between 0 and 1. So what that means is that for any event A, the probability of A has to be between 0 and 1 inclusive, meaning that probability of A can be 0, it can be 1, and it can be anything in between. And this will help us later, as we'll see, because this concept that all probability must be between 0 and 1 helps us to sometimes be able to solve in equations for missing variables. Okay, so this is showing you that same concept, but just on a number scale here, with an event at 0 being impossible, an event here being unlikely, here a 50-50 chance, so at the 0.5 point between 0 and 1, then an event that's likely, and at 1, an event that's certain to have happen. Okay, a couple other things that we need to touch on before we continue on with our discussion of probability. The next is complementary events. So the complement of any event A is denoted by A with a bar over it, and that consists of all outcomes in which the event A does not occur. So essentially you have event A, and then you have not A. And between the two of those, that is all the different possibilities that can happen. Because you can't have both event A and not A. It really has to be one or the other. And not A, or A with the bar over it, is considered to be the complement of event A. So here's an example. 1,010 United States adults were surveyed, and 202 of them were smokers. So if we go back to our probability event, or our probability equation rather, we're going to find that the probability of being a smoker, if we take our 202 people that were smokers and divide that by the total number of people that were surveyed, we find out that our probability of being a smoker is 0.2, or 20% if you were to multiply that answer by 100. So then it follows that your probability of being not a smoker is 1 minus your probability of being a smoker, which is 0.8. And together, between 0.2 and 0.8, they add to 1, which we know by definition must happen based on what we saw right here. That probabilities always have to be between 0 and 1, and together, an event plus its complement must equal 1, which is exactly what we have in this case. The event is being a smoker, and its complement is not being a smoker, and when you add them together, they add to 1. Rounding probabilities, let's talk about that a little bit. So when expressing the value of a probability, either give the exact fraction or decimal, or round off final decimals results to 3 significant figures. So this is something to note as this will become important for the exam as well as for my math lab, that with probabilities it's always 3 significant digits. So their suggestion is when a probability is not a simple fraction, such as 2/3 or 5/9, express it as a decimal so that the number can be better understood. All digits are significant except for the zeros that are included for proper placement of the decimal point. So if you're not as super familiar or haven't done anything with significant digits in a long time, I recommend that you practice this, and if you need any help with this, please reach out to me. Okay, a couple of other things. An event is unlikely if its probability is very small. And in math, we define very small as being 0.05 or less, which is 5% or less probability. So an event has an unusually low number of outcomes of a particular type, or an unusually high number of those outcomes if that number is far from what we typically expect. So again, an event is considered unlikely if it occurs 0.05 or 5% of the time or less. A couple of other things to touch on. Odds. So in probability, sometimes things are expressed as odds. So the actual odds against event A occurring would be the ratio of the probability of not A over the probability of A. And it's usually expressed in the form of A to B, where A and B are integers having no common factors. The actual odds in favor of event A occurring is the ratio of the probability of A divided by the probability of not A, which is the reciprocal of the actual odds against. So these two equations are just opposites of one another. And here, if the odds against A are A to B, then the odds in favor are B to A. Something else worth noting here is what we call payoff odds. Payoff odds are the ratio of the net profit if you win to the amount bet. So the way that that's expressed is that payoff odds against event A equals your net profit with a colon to the amount bet. And as we'll see with some of the casino examples that we'll see, payoff odds come up in a few different places within probability. So here's an example where we have payoff odds. So we're going to bet $5 on the number 13 in roulette. And our probability of winning is going to be 1 in 38 because there's 38 different possible numbers in roulette. And the payoff odds are given to us by the casino at 35 to 1. So we want to find the actual odds against the outcome of A, because we have the odds of A, which is 1 over 38, but we want to find the actual odds against the outcome of 13. We want to know how much net profit would you make if we won by betting on 13. So here, first in part A, we're going to find the actual odds against the outcome of 13. With the probability of 13 equaling 1 over 38, and the probability of not 13 being 37 over 38, because that's how many other options there are. If there's 38 total options and one of those options is 13, then it serves that 37 of those options are not 13. So the actual odds against are going to be our probability, if we go back to our equation, our probability of not 13 divided by our probability of 13. So we simply will plug it into the equation. 37 over 38 divided by 1 over 38. So again, probability of not 13 divided by the probability of 13 to wind up with odds of 37 to 1. Because the payoff odds against 13 are 35 to 1, we have the following. There's a $35 profit for each $1 we bet. And since we bet $5, there is an $175 net profit. The winning bettor would collect $175 plus the original $5 bet. Okay, that ends section 4.2 on basic concepts of probability. Up next, section 4.3 on the